Andreas Olofsson. Many of you probably know him. He speaks about SiliconCompiler, which is made for Silicon. Thank you very much.
All right, thank you. All right, this is fun. I've been, working too much lately, and I was kind of tired. But then I got here and I got energized. So this is awesome. I love this group. There's my email if you ever need to reach me. It's just my first name. Let's see. Okay, so this is my origin story in open source, how I got involved. So 98 to 2008, I was at Analog Devices, all proprietary tools. And, I never really worried about it. Somebody else did that for me. But then I started a company in 2008. And, the first thing I realized was, okay, well, I've got no EDA tools. How do I write my Verilog code for my new processor that I'm really excited about? And I sat in that basement right there in my home and called Model Sim and asked him, okay, so how much for a VCS type license? And he's like, all right, $5,000 or something like that. Like, well, I'm not doing that. And then I remember Googling free Verilog simulator, right? And I find Verilator, right? And so that's how I got going, and it was good enough, right? It was literally like I didn't miss a beat, right? So we used the commercial one, and then I had free. So so that's how I got started, and it was eye-opening. It didn't do everything though. So one of the things I learned was that the things that I could do in a closed simulator, like use latches, right, and dynamic logic and all kinds of cool stuff, didn't quite work, right? So this is Wilson, and Wilson Snyder's awesome, right? And so he lives in New England. So early on I had lunch with him, and I submitted an issue like, all right, how do we do this? And he's like, well, I don't think we can support that, right? So if you look at this thread, he's like, all right. And then I was really happy to see in March, what is that, May 15th, 2022. So that's a little bit longer latency than I would like for a bug fix, but got fixed, right? So never give up. But clearly I came up with a workaround in the meantime. But I thought that was awesome. So this is the team right now, and the outline in pink are the ones that kind of work on this project, and the team has been growing. So somebody asked, like, okay, how do you make it work, right? How do you get to work full-time open source? And I think we've figured out a way at least. So let's say about half the work we do is open source, and happy to talk about that offline. But definitely you need to find a sponsor for your work. And just tiny plug, we're hiring, right? So just so you know. So the problem we want to solve, right? And SiliconCompiler is just part of it. Is reduce the barrier to silicon, and automation is part of that. Better use of IP, reuse is another part of that, right? So, so this is the demo. So if you have your laptop out, I'm kind of hoping you'd help me out with something. And if you haven't tried this yet, just do pip install SiliconCompiler, right, at the command line, and then just run that little demo line there, sc-target asig demo-remote. And that's going to kick off a job to a server somewhere in AWS, which has got all these open source tools installed: Sherlock, Yosis, OpenRoad, KLayout, the Sky 130 PDK. It's got a SLRM scheduler up there. And if you run that in a couple of minutes, you should get a picture popping up on your client with the actual layout, right? In this case, it's not going to send back GDS because we wanted to save some money in the egress of the data. But if you were to run this locally, you would get the whole GDS, of course. So this is the SiliconCompiler, kind of like how it works, or how you can use it. So what is it? It's kind of make for silicon, right? So this is not the hard stuff. This is not an EDA tool. It's not a compiler. This is literally just your bash script, your makefile, which may not seem very difficult, but it's still better than this, right? So this is the status quo in the industry. Let's just take a reference methodology from one of the EDA vendors, and just a monolithic blob, and let's just Control-C and Control-V that until we die, right? Just derivative after derivative gets uglier and uglier, and so how do we solve that, right? And that's what we're trying to do here. And we're not the only ones who are trying to solve this, right? There's a lot of framework. There's FuseSock, there's Edelweiss from Olaf, there's Hammer from Berkeley, and many others. So this is our take on it. But I think we can all agree that we should not be and this is another example, right, from a great project, right, Ariane from Florian and ETH Zurich. We should not be writing make files, right? So here's my first poll. How many people in this room like writing make? That's too loaded a question. How many people in this room know how to write make files? Okay. All right. You're not normal. Okay. This is not. You shouldn't assume that this is normal. So most people do not know how to write make files, and so we should not be doing that. Right. It's a barrier. So Python is much friendlier. So this is the platform, and it was created to work well with open source and proprietary tools and proprietary PDK. So trying to be pragmatic, right? We can't be open source or nothing. We want to be, the designers should always see an open standard. So one of the biggest problem with the commercial way of doing things is NDAs, right? And lock-in APIs, right? So for example, you create a design course, and you teach, you show some scripts or something like that with an E tool. You may not be able to share that script that you created. You wrote the script, but you can't share it with anybody. That's not right. And so we want to make sure that at least the API that the students and the teachers and the designers and everybody interfaces with is completely open. So that's where the Python API and the schema fits in. Now below that, the actual content may not always be open source. If you're going to use a 3 nanometer PDK, that's very unlikely to be open source anytime soon. So we have to be able to deal with that. We work with commercial tools, and while we may want for them to have open APIs, they're not open, so we will have to deal with that as well. So just having that kind of dual approach like we have in Linux, right? For Linux, you can have a Mesa, GPU driver, a graphics driver, or you can use a proprietary NVIDIA one, right? But all fitting into the same distribution. So that's the approach we had, and so basically it's kind of a make system, so to speak. And so this is what we want to present to the designers. This is what I think design should be like. Since we created this, I really enjoy using the system. We use it for all our tapeouts. And so basically, you import the SiliconCompiler package from pip, and then from there on, it's kind of just all Python code, right? So you create a chip object, right? In this case, Heartbeat is my top-level design. I start defining like all the parameters statically, right? What are the inputs? What kind of design constraints? There's about 325 parameters right now that you can define, that you can look at in the docs. And then once, you load a target, so you have a way of kind of bundling these things into an easy, compiler-like target. Just like you would compile for, RISC RV64GC, right? That could be a target. So same thing here. You have a bundle of things that set constraints. And then after you've set up everything statically, you just go run. So the reason behind the run command is we want to be able to run it everywhere. And that was kind of the simplest way we can think about it, is just a simple run command. After you're done, you can inspect it, do a summary, show the layout. So so this is, we want to stay within Python for design. So there's a few ideas I want to talk about here. None of them are particularly novel, but I think they keep coming back, so we should just repeat it. So one is this resolving this n-squared problem, right? So translation, right? Your pandoc for, there's so many formats. We need to have an IR that can translate all to all. It's an incredibly powerful concept. And you may not know this, but going back to the early 1980s and the first VLSI revolution and Mead and Conway, the GDS format, right, which we today take for granted. Before there was GDS, there was a complete disaster, right? There was no interoperability. You had to basically produce a CAM file for every foundry instead of having this data. You can have a set of design rules and a GDS file. So, let's do this as much as possible wherever we can. And by the way, in the industry, it's not like this, right? Because every EDA vendor has its own API, right? So you can't do that. So you have to way of abstracting that away. Second one is, let's have a schema or a database for interchanging information, right? So that can be protobuf, JSON, YAML, whatever. We decided on JSON, and I really feel this very strongly. Don't abuse YAML or JSON, right? If you have to Google, how do I put comments in my JSON? You're not doing it right, right? So that's why we believe that everybody should be designing using Python, and this is just a data interchange format, right? And I strongly believe that. YAML doesn't scale in complexity. It looks great when you're doing 10 lines, but when you have hundreds of lines of codes, which you, for a complicated project, you will get to, then you want the looping constructs, the comments, the functions, the object, you want all of that from Python. You don't have that in JSON or YAML. So this is our, but we do believe that there needs to be an ASCII formatted database in the bottom, and for us that is a schema. And it's not the prettiest thing, but it is fairly human readable and certainly storable and exchangeable. The second one is design manifests, right? So when you do a synthesis, place and route, or spice simulation or whatever, you're doing something on the design, you're running a tool, and today there's no standardized record for doing that. We kind of do our work, and then we tar up the directory or we zip it up, and that's what happens. Or we just keep a record of what we did in our head. And the idea of actually tracking what we did is very powerful. Now you can have provenance, you can have better handoff, you can have test cases, right? So the best way to get a user to just go away is, can you submit a test case for that? And then, nobody submits a test case because that takes time. What if you can automatically extract the test case, right? That's a very powerful thing. So design manifest today does not exist in the industry, and it's definitely needed. The next one, which is one of the main reasons why we have all this funding, is design provenance, right? How do we actually have trust in what we designed, right? Where did it come from? Is it secure? And so by having this manifest and this automated way of tracking what is done, we add security to the process. And again, doesn't exist today when you have a non-structured makefile with people just typing commands and no records. There's no provenance whatsoever. You just basically have to draw a big circle around everybody in the company and say, okay, you're all now in a cluster. You only log in over VNC, and maybe you have a key, keystroke logger or something like that inside that wall, and everybody's under NDA, everybody's an employment NDA. That's how we trust things, right? So that in the government that may be called guards and guns, right? Is the way of protecting your stuff, not by actual provenance. And then leading in further on this standardization, standardizing on the metrics, right? So again, there's lots of log files that come out of the EDA tools, right? And there's usually unstructured text. So if you have 3 EDA tools or 10 EDA tools, you start writing little Perl scripts and grep logic. And I've done this since 1998, and I want to puke every time I think about the nonsense I've done there. Wouldn't it be great if you can just do that once, put that into a structure, and then since these things are all the same, right? We're all grepping for the same thing with slightly different wording. Put in the data structure. Now you can just do chip.get with a keyword that never changes, and no matter what design was run, what tool, it's just there. And then that's a great abstraction for people who, let's say, want to do machine learning or run some kind of sweep on the design. They can now just work at the Python level and calling those keywords rather than ever having to worry about the EDA tools formatting of their output reports changing and having to change your grep logic. And then the next idea is this client-server model, right? So tools in general, right? Commercial tools generally only run on Linux, and they only run on Red Hat version whatever. I've run those tools in Ubuntu since 2008. They work, but I can never tell the EDA vendor that I'm running in Ubuntu, because as soon as I do that, no, there's no warranty. We can't help you now, right? And so there's a problem with installation and support. Open source tools may be even more complicated. So I think the idea that there's millions of clients running these things. They may be running on Apple, or Mac OS, on Windows, on Linux. They may not be very well versed in running Make or CMake or running Docker. We want to make it as easy as possible, and the way to do that is install everything on a server and then connect to that server remotely. And the last one is, Make is not really scalable, right? You may be able to run multi-threaded on one machine, but it certainly can't take advantage of warehouse scale computing. So we need to be able to take these graphs, right, of steps that we need to do in complicated flows and be able to execute them. Now, fortunately, with EDA tools, they're so slow that we don't really have to worry about performance, right? Our message passing paradigm can be very primitive. We can do things like file-based communication. So, in our case, we created a very primitive programming model with nodes and edges, a static graph. And then, we send that graph to the run routine and just say, go, take care of it, right? And then you can schedule that on your local machine. We can schedule that in the cloud using SLRM. But basically, by having such a ridiculously simple programming API, where the call is run and a static graph, it gives a lot of freedom to schedule wherever we want. Last idea, I think, is the auto-generated documentation. So we kind of built in documentation from day one. We put everything into the schema, and then we use this, simple things around Sphinx to make sure the API is documented. I highly recommend it. Think about documentation from day one. It's good for you and for everybody else. We're at about 380 pages and counting right now. The one thing that we kind of tripped us up, though, is we thought the reference manual would be enough, but then we started getting a lot of complaints that, oh, there's too much documentation. It's 380 pages, right? And so you have to structure it so to make it, okay, you need the get started guide, you need the examples, and then you need the 380 pages of documentation. You need all of it. So it's a total end function. You need to do every single step or you still fail. So we're kind of patting ourselves on the back for a few months and realized that we had gaps still, right? So, and the last thing I think is that's the billion-dollar idea that somebody should pursue is ChatGPT for open source projects. I mean, come on, the code is there. Can't somebody just auto-generate the cool documentation? Seems doable. So what's the success so far? So we've been doing this for a while now. We actually launched it in December 21 publicly. It has some pickup, not nearly enough as much as I would have hoped for, but we have been using it in-house since day one. Taped out 3 chips in the fall, in the span of 8 weeks, with 6 people more or less, so that's about 2 people per design. So a GF12LP, this is an advanced FinFET design, 2x2mm chips, this is fast, right? And some of this RTL code was written while we're doing this. So this is 8 weeks while doing RTL, ramping up new flows, a CPU, an FPGA, and a memory chiplet. I'd say this is a good testimonial for the SiliconCompiler, and everything was done through the same infrastructure. So the flow, of course, that flow, because GF12LP is not fully supported by OpenRoad yet, we use the commercial tools, and this kind of shows the implementation graphs that we had for running all the steps, and of course all the people involved used the same tools, which made it very easy to collaborate between the different chips. And this kind of also shows that you can easily mix and match, right? So every task, right, every bubble here can be a different tool. So if you want to, mix and match, layout, synopsis, cadence, whatever, not really a big deal because the interfaces between those tools are fixed. So this is our, SiliconCompiler bingo. Kind of like, this is the whole point, right? We want to have all the EDA tools and all the foundries at the end of the day, all green. That's the goal. For now, we've got Intel 16, GF12LP, Sky 130, and some FOSS tools, some EDA tools done. And that Intel 16 tape out with FOSS was not done by us. It was done by somebody in the U.S. government. So last week we kind of did a mini relaunch. We realized there were a couple of barriers to adoption. One was we had the server turned on in 2021, this remote server concept, but we had a login barrier, right? So we asked people to register, and that seemed to be a big turnoff, right? And so we said, okay, fine, we'll turn off all barriers. We'll give it away to everybody for free. You just basically, do pip install, and then you're ready to go. And then it if you do the -remote option, it just goes to our server address and just runs it. And so this is now us doing like, the app way, we giving away cloud compute for free. So now we have something that's no money barrier for anybody. It's basically free, no registration barrier, time barriers, pip install SiliconCompiler. I mean, that's like 2 minutes or 30 seconds. And so pretty good. We had, 459 compilations last week. We got this, which I thought was pretty cool. So we started, I posted this on LinkedIn, and this totally made my day, right? Because I saw people using it. The thing I hate more than anything else is like working hard and then having it not matter, right? So having like you work so hard on a code base, you release it, nobody comes. And who was it that said this? This is Scott, right? Build it and they will come, right? So you build it and then nobody comes. It's extremely disappointing. So in this case, people actually started running it, right? And so initially it was just running the canned demo, and then people started putting in their own code, and it worked, right? More and more people piled on, and they worked on Mac, it worked on Windows, it worked on Linux, and then by the end, I think the coolest result was Steve Hoover, who some of you may know. He's kind of part of this community. He's got this thing called MakerChip. So he was teaching a class, and he had his student hook up the design they're working on in this programming language they have to create an ASIC, right? And so I think this was shows what can happen when you make it easy enough and you get people on board. So that's sort of the SiliconCompiler, and I'm going to we just push in. I think the community in itself, if I go back to 2008, 2008 there was almost nothing. There was kind of like Icarus and Verilator, sort of, right? That was the community. And then 2017 I went to DARPA, and it was a lot better, but it was still pretty rough. It's moving very, very slowly, but we're definitely making progress. So I always track these things because it's getting to be a lot to keep hold on. So there's now well over 300 really good projects out there in open source that you should be aware of. So just go to this list, or just put in your repo there, and I'll add it, that way we can kind of keep track of what's going on in the community. So thank you.
Thank you. Questions?
I love your awesome hardware list. That's a great page. Sorry, just a little thank you for that.
Can you speak to how the portability layer for like SRAMs and synchronizers works in this kind of flow?
Portability layer. Okay, for different PDKs, right? Or yeah. So that's if you don't have any SRAM synchronizers, pretty easy, right? That's one. So I think what you saw there, like people were putting in RTL code, right, for adders and things like that, and it works really well. So what I've always done is I've had a little shim layer where I'll abstract away, and then I'll have like a hash defined that will say which node I'm at, and then I'll pick something. Yeah, so we have a compatibility layer, right, that we're going to open source at some time. I don't know, maybe I'll make it today. But we have, I think that's the answer. You have an SRAM compatibility layer, you have a standard cell or something like that, and then your users will just have to use that cell, and then there is some runtime or link step that pulls in the right cell, gotcha. Which if it's open source, that should be okay, right? So I mean, yeah.
So today I'd have to like hard code my SRAM, but
tomorrow.
I'm sure there's tomorrow.
Yeah.
Okay.
Yeah.
Hi, Andreas. With the new flow that you've got that are getting lots of success with, what's blocking you getting them to the final stage of submitting something, to the MPW program to actually get their silicon made?
Probably ease of use, right? Hooking that up into the shuttle program. So we don't own that effort, right? And so I think I don't see any blockers to why you or eFabless or somebody couldn't take SiliconCompiler and integrate it into your flow. should be doable. I mean, Wenting did that last year, right? For his chip. So I think, yeah, no blockers.
So tomorrow.
Well, I mean, like, I'm not going to do it. Like, it's just time and labor, I would say, is the thing, right? So.
How do you add new tools? Like in the GTS Adre framework, we've been adding like FEM solvers and other TCAD plugins. If you want to get something installed on your server, how do you add it?
So there's two components. One, there is the see if I can get out of this mode. Okay. So, okay. Oh. Okay. Yeah. So, so if we go into the repo, the way we bring in new tools is we have a, and we try to partition it so it's kind of well encapsulated. But if we take a tool like what do we want to take? Sherlog. So this, every tool has its own directory, and every tool needs a setup script or setup definition for the tool itself, which is generally very simple. That will define kind of like what are the like in this case, what's the name of the executable, and what's the version number, right? And a couple other things, right? So that's how you define how to call the tool, and then you also have to define what's the task, right? And what do you do inside that task? So a tool can have many tasks, right? So OpenRoad, for example, could have a task that's CTS, a task that's routing, right? So you have the basic executable setup, and then you have the basic what will it do, right? And so you kind of the task is kind of defining a function for hooking it up. So, what for Sherlog, at the end of the day, you're not really defining a program for Sherlog. So Sherlog is a command line executable. So really all you need to do here is set up the command line switches to that program. So we, in this case, we use Sherlog as a Verilog import stage and a pickling stage. So it's not really very much. Let me see if I can bring up the OpenRoad as a better example of what could be done. The thing is that when it does get complicated, right? And that's the thing, right? To be careful with. If something's complex, it may not always have a trivial, answer. But in this case, the routing step is just a pass through. What I wanted to show was actually since OpenRoad is a tickle-based tool, and this is one of those architecture or design decisions. We decided not to try to emit tickle from Python. So by emitting tickle from Python, you're kind of working at the command layer, and a lot of the tickle scripts I've seen from commercial vendors or from large semiconductor companies can be 10 to 20,000 lines long. And so at 10 to 20,000 lines, it's source code, right? You're going to have revision control and all of that. So the way we did it, instead of trying to emit tickle code from Python, we basically have a source file here that we call, and then that source file has an interface to it, which is handled by the schema, which does the handoff of parameters and choices, right? But you can always go in and modify the tickle file. So one way to create your own flow would be create your own OpenRoad flow scripts, if you like. And so a new tool like a solver or something, if it's command line driven, fairly simple interface. If it actually has an API and tickle command, you'd probably want to write your own thing. Okay.
So I noticed that the runtime for each of these 3 example chips were less than 24 hours. Does that mean that your old DARPA mission of 24-hour no human in the loop is now accomplished?
Well, so not. I mean, of course not. The answer is no. But if you look at the difference, right? So the chips that we did in 24 hours, they all had the same floor plan, right? In a way, like or at least part of it, right? And so then also the question is, what do you count as 24 hours? So the DARPA goal was take any RTL and then spend no time writing tickle code, spend no time floor planning, and just push the button and you get a GDS out. Here, I mean, there was 8 weeks of floor planning and design and RTL and co-design and all of that, right? So it was really like 8 weeks, not 24 hours. So there's still a long way to go. And I know the Open Road team is working on it still to go that last piece of, okay, can I throw any kind of RTL and just have the tool be smart enough to produce me a proper layout?
Just a quick question from me, Andreas. Do you intend, and possibly you already said this, but will you support proprietary tools with this flow as well?
Oh, we do. Yeah.
You do?
Yeah.
Okay.
Yeah.
All right. Good.
Except we can't distribute those tools.
Indeed, but you could have the kind of shims in the central repo, right, to invoke them?
Not clear.
Okay.
So with the vendor's permission, we could.
Yeah. Okay.
Are you pushing for any commercial adoption in any of the CAD groups in all semiconductor companies?
If we're pushing for adoption, or
like I have done this in my time when I was with you in ADI in San Jose, but so I was in Intel last time, and we have a similar framework internally, and I think every company has their own framework. Are you trying to like sell it or like propagate it in different, because it will, as for designers, as a CAD guy, I'm trying to make the life of the designer easier. I think that's the goal, and we are all trying to reinvent the same wheel, and this is a great tool, and if everybody adopts the same thing, it will be much easier. And the good thing about here is you have on the back end the 3 major tools and Open Road. So if you have to do a comparative study, it's very easy.
Yep.
So.
Yeah. So this, I mean, this is freely available, right? So there's nothing stopping any of the large semiconductor companies from doing this tomorrow, right? Now, when we were at DAC in July, a person from a large semiconductor company stopped by our booth, and they understood what we were doing, and he basically said, "Oh, so you're trying to take my job away from me?" So there's, I mean, so depending who you talk to, right? So, I mean, everybody's, has maybe an environment existing. They're trying to get do a job. If you're in a CAD group at a large semiconductor company, you may not want to go use an open source tool, right? If you're a designer, you may want to, but the question is, right, how do you make that happen? So we're putting it out there. We talk to whoever we can, right? But this is not our product. Our product is chips. So we're like one of those large semiconductor companies, except we're giving away our CAD environment for free.
Awesome. There's a question, Tim. Last question.
I was wondering if you have any plans around interop with other flows, say, so that you can move, part of your flow over to SiliconCompiler, and as new stuff comes along, incrementally adopt it rather than adopting it all in at once.
So, we have to be a little bit selfish. Sometimes too, right? So we have to get our chips done, and sometimes we spend a little bit too much time working on stuff for fun or just for the community, but we got to get our chips done. And so if it's something that's not on that path to getting our chips done, we're not going to do it. So right now we're completely invested in SiliconCompiler. Our flow is, we write RTL Verilog. We use commercial tools for taping out, right? Because that's what we need. So if it's something that's another framework, it probably won't get done, to be honest with you.
So I recall you had something around like a makefile compatibility thing for some period. Is that no longer happening?
So what happens is that I say that, but then something always comes up. We're like, well, we're not ready to move on to SiliconCompiler, but so we've created compatibility layers with Cadre in ORFS and OpenRoad. That's one thing we did. We created a really ugly conversion script from makefiles to SiliconCompiler for a commercial EDA vendor. So we have done things like this, but it's not like, it's like we write it and then we're like, no, not supported, right? We're moving on. So
awesome. So let's thank Andreas again.